In 2020, Voyager 1's magnetometer registered a sudden jump in the strength of the magnetic field surrounding it, 14 billion miles from Earth, in the supposedly empty space between the stars. That kind of jump had happened before. Scientists had a working explanation for it, and they expected it to fade within a matter of months, the same way it always had. It didn't fade. As of a study published in 2026, that elevated magnetic field has now persisted for more than 5 years, still measurably active, still refusing to return to normal. And the scientists tracking it are on the record saying the mechanism that's supposed to explain it doesn't actually explain what they're now seeing. Everybody, this is the real, ongoing, still unresolved story of what Voyager 1's instruments have been recording in interstellar space, not manufactured drama, not alien megastructure speculation, but a genuine, peer-reviewed puzzle that's been quietly building in the scientific literature for half a decade. And it's still not solved. Let's start with where Voyager 1 actually is, because the location itself is the entire reason this story is even possible. Launched in 1977, Voyager 1 is the most distant human-made object in existence, and in August 2012, it became the first spacecraft in history to cross the heliopause, the boundary where the sun's bubble of solar wind and magnetic influence, called the heliosphere, finally gives way to the true interstellar medium, the thin, cold material that fills the space between star systems. That crossing was confirmed through a combination of signatures, a sharp increase in galactic cosmic rays reaching the spacecraft's instruments, a corresponding drop in particles associated with our own sun, and, critically, a measurable jump in plasma density detected by Voyager's plasma wave instrument, first documented in April and May of 2013, when researchers finally confirmed, through careful analysis, that the crossing had genuinely occurred nearly a year after it actually happened. That delay itself is worth understanding, because it illustrates just how difficult it actually is to study this specific environment, even with a spacecraft sitting directly inside it. Voyager 1's plasma detector, the instrument that would have most directly and immediately confirmed the density change associated with crossing into interstellar space, had actually stopped working decades earlier, damaged during the spacecraft's flyby of Saturn back in 1980. Without that instrument, researchers had to instead wait for a fortunate indirect opportunity, a solar eruption powerful enough to send a detectable pressure wave all the way out to Voyager 1's position, exciting the surrounding plasma into oscillations that a separate, still functioning instrument, the plasma wave subsystem, could actually detect and measure. That indirect measurement, arriving via a lucky solar event nearly a year after the actual heliopause crossing, is what finally let scientists confirm with confidence that Voyager 1 had genuinely left the heliosphere behind. It's a detail that foreshadows exactly the kind of patient, indirect, painstaking work that continues to define how scientists study this specific spacecraft's data to this day. Since that crossing, Voyager 1 has been humanity's only direct physical sensor sitting in the space between stars, sending back real measured data from an environment no other spacecraft has ever sampled. Here's what makes that position scientifically valuable beyond simply being a record-setting distance. The heliosphere isn't a rigid, fixed bubble. It's constantly being pushed and reshaped by the solar wind, the stream of charged particles our sun continuously emits, and that solar wind's intensity rises and falls across an 11-year solar cycle as the sun's own magnetic activity waxes and wanes. When the sun goes through a particularly active phase, it can launch especially powerful surges of plasma outward, sometimes in the form of coronal mass ejections, enormous eruptions of magnetized plasma blasted away from the sun's outer atmosphere. And if those surges are strong enough, they can travel all the way out to the edge of the heliosphere and beyond, physically pushing on the boundary itself and sending a kind of pressure wave rippling into the interstellar medium surrounding it. It's worth appreciating the scale involved in that journey. The heliopause sits well over 100 astronomical units from the sun, meaning any disturbance generated by solar activity has to travel that same enormous distance before it can have any measurable effect on Voyager 1's surroundings, typically taking well over a year to complete that outward journey even while moving at tremendous speed. Voyager 1, sitting out past that boundary, has been in a genuinely unique position to directly detect exactly what happens when the sun's activity reaches that far, a real-time sensor, documenting how much influence our star actually has on the space immediately outside its own bubble. That's a genuinely rare scientific vantage point. Every other instrument humanity has ever used to study the sun's influence on its surroundings, whether solar telescopes, satellites orbiting Earth, or probes studying the solar wind closer to home, sits well within the heliosphere itself, measuring the sun's direction. T-effects rather than its indirect second-hand influence on the true interstellar medium beyond. Voyager 1 alone offers a genuine physical measurement of that boundary interaction from the far side, a perspective nothing else currently operating anywhere in the solar system can provide. This isn't the first time Voyager 1 detected this kind of transient magnetic disturbance. Researchers had already documented similar events before 2020, including 2 significant jumps in interstellar magnetic field strength. Recorded back in 2012 and 2014, not long after the spacecraft first crossed the heliopause. Those earlier disturbances followed a pattern astronomers had come to expect: a relatively sharp spike in magnetic field strength, followed by a period of elevated but gradually declining readings, before the field eventually settled back down to its previous baseline level within a matter of months. Notably, both of those earlier magnetic jumps were also preceded by distinctive plasma oscillation events, exactly the kind of signature associated with a shock wave passing through the surrounding medium, giving researchers additional independent confirmation that these disturbances really were being driven by an outside pressure wave arriving from elsewhere, rather than some purely local, unrelated fluctuation in the immediate area around the spacecraft. Adam Sabo, an astrophysicist at NASA's Goddard Space Flight Center and the principal investigator for Voyager's magnetometer instrument, described the underlying mechanism researchers developed to explain this pattern in a simple, memorable way. He said the source is essentially like a piston, meaning that when the sun releases a strong surge of solar wind, that surge takes over a year to physically travel outward and slam into the boundary of the heliosphere, creating a compressive wave that reverberates into interstellar space, temporarily intensifying the magnetic field and plasma density in the region where Voyager 1 happens to be sitting. It's a genuinely elegant, physically sound explanation, well supported by the earlier data, and it worked for a while. If a real, currently unresolved scientific mystery like this, documented in actual peer-reviewed research rather than exaggerated online speculation, is exactly what you come here for, subscribe now, because understanding exactly how this specific event broke that established pattern is where the real story begins. Because in 2020, Voyager 1's magnetometer registered another one of these jumps, and at first it looked like exactly what researchers had already seen before. The magnetic field intensity increased, plasma density rose correspondingly, and the piston model predicted this event should behave the same way that 2012 and 2014 disturbances had, a temporary spike, followed by a gradual return to baseline within several months. That's not what happened. As detailed in a study published in 2026 examining Voyager 1's magnetic field data from the onset of this event, nicknamed the magnetic hump, all the way through mid-2025, researchers documented that the elevated field strength simply never fully subsided. Instead of a several-month disturbance, this event stretched on year after year, continuing to register elevated sustained magnetic field readings well beyond anything the original piston model had prepared researchers to expect. The specific numbers researchers tracked across this extended period are genuinely striking. From mid-2024 alone, the study documented magnetic field strength that decreased to 0.45 nanotesla in late 2024, then rose back up to 0.5 nanotesla by the end of that year, before stabilizing at approximately 0.50 nanotesla through the first several months of 2025. Following a gap in the data, the field then decreased again to 0.47 nanotesla by mid-2025. Over that entire stretch, dating all the way back to when this specific pressure event first began in 2020, Voyager 1 itself had physically moved outward from approximately 149.3 astronomical units from the Sun to roughly 167 astronomical units, meaning the spacecraft covered a genuinely significant amount of additional distance, nearly 18 astronomical units, or over 1.5 billion additional miles, while this single magnetic disturbance remained active the entire time. The study's own authors stated the conclusion plainly, noting that such strong and spatially extensive magnetic fields had never previously been observed by Voyager 1 at any point across its entire mission. Stop and actually sit with that specific detail, because it's the crux of why this genuinely matters. This isn't a disturbance that lingered for a few extra weeks beyond what models predicted, a fairly unremarkable margin of error in a complex physical system. This is a magnetic enhancement that has now remained measurably active for more than 5 years, spanning a physical distance of well over 1 billion miles of Voyager 1's own outward journey, in a region of space that, according to the working model researchers had relied on since the previous 2 disturbances in 2012 and 2014, should have returned to normal, quiet, baseline conditions within a matter of months. The scientific community's own reaction to this extended timeline is documented directly in the research literature. And it's worth quoting precisely because it captures the genuine uncertainty at the heart of the story. As reported in coverage of the ongoing investigation, researchers noted that the anomalies which began in 2020 did not abate, and that this persistence led some mission scientists to seriously question whether the disturbance actually originated with the Sun at all, the same fundamental assumption underlying the entire piston model that had successfully explained the 2 previous events. That's a genuinely significant admission. It's not simply an acknowledgement that the timeline ran a bit longer than expected. It's professional astrophysicists, directly involved in analyzing this data, openly entertaining the possibility that the source of this specific magnetic enhancement might not be the sun's solar wind pushing against the heliopause at all, but something else entirely. Something happening within the interstellar medium itself, in a region of space humanity has never had a direct sensor stationed in before Voyager 1 arrived. It's important to be precise here, because precision is exactly what separates honest reporting on a genuine scientific mystery from irresponsible speculation. Researchers have not concluded that some unknown exotic force or structure caused this event. The leading, most extensively studied explanation remains a variation of the original piston model, just one requiring meaningful refinement to account for why this specific pressure wave has proven so much more persistent and spatially extensive than the two that came before it. The 2026 study specifically ties the origin of this extended disturbance back to solar cycle 24, an unusually active period of solar activity, proposing that the particularly strong magnetic fields generated during that specific solar cycle are what's been driving the heliopause outward against the surrounding interstellar plasma with unusual sustained force, functioning like a piston that, in this specific instance, simply kept pushing far, longer, and far harder than the two previous events had. Because the heliopause's response to changes in solar wind conditions measured near Earth is typically delayed by 1 to 2 years, as that disturbance physically travels outward across billions of miles, researchers have had to carefully account for that lag time when trying to match this extended magnetic enhancement back to specific periods of heightened solar activity. That refined explanation is genuinely compelling, and it represents real, serious, ongoing scientific work being done by researchers actively trying to understand what Voyager 1 is recording. But it's also worth being honest that, as of the most recent published research, the picture isn't fully, conclusively closed. The same 2026 study that proposed this refined, solar cycle 24-driven piston explanation also documented additional complexity within the data itself, noting that following the heliopause crossing, the direction of the magnetic field measured by Voyager 1 showed only slow, gradual changes across an extended stretch of this event. A detail researchers are still working through as part of building a complete, physically consistent model of exactly what's happening in this specific region of the interstellar medium. If genuinely unresolved, real scientific puzzles like this, the kind still being actively investigated in peer-reviewed research right now, are exactly what you come here for. Subscribe now, because there's a broader decade-long pattern of magnetic field anomalies connected to this specific spacecraft that makes the current mystery even more interesting to place in context. Because this isn't actually the first time Voyager 1's magnetic field readings have puzzled scientists since the spacecraft crossed into interstellar space. Back in 2015, an entirely separate magnetic anomaly generated real uncertainty within the scientific community, this time concerning the actual direction of the interstellar magnetic field Voyager 1 was measuring, rather than its overall strength. For roughly 3 years after its 2012 heliopause crossing, some scientists genuinely questioned whether Voyager 1 had actually left the heliosphere at all, because the direction of the magnetic field it was recording didn't match predictions based on other independent measurements of the surrounding interstellar medium. A team, led by Nathan Schwadron at the University of New Hampshire, eventually worked out an explanation published in the astrophysical journal Letters and confirmed directly by NASA. Using data from NASA's Interstellar Boundary Explorer, or IBEX, a separate mission that had discovered a distinctive ribbon-shaped structure of energetic neutral atoms in 2009, believed to trace the true direction of the pristine, undisturbed interstellar magnetic field, Schwadron's team determined that Voyager 1 wasn't measuring some anomalous, unexpected field direction at all. It was measuring a real, physically distorted magnetic field, bent and deflected by its proximity to the heliopause itself. Schwadron offered a memorable, genuinely useful way of picturing the physics involved, comparing the interstellar magnetic field near the heliopause to a rubber band stretched around a beach ball, with the field lines bending and draping around the heliosphere's outer boundary the same way that rubber band would wrap around and deform against a spherical obstacle. The study predicted that as Voyager 1 continued moving farther from the heliopause into progressively less distorted, more pristine interstellar space, the measured field direction should gradually rotate to match the true, undisturbed direction traced by the IBEX ribbon, with that transition expected to become apparent by around 2025. That earlier mystery, fully resolved through careful, patient, multi-instrument scientific work, combining Voyager 1's direct, in-place measurements with IBEX's independent remote observations, offers a genuinely useful template for understanding how the current magnetic field strength puzzle is likely to eventually get resolved as well. It probably won't be settled through a single, sudden revelation. It's far more likely to be gradually, carefully worked out exactly the way the 2015 direction anomaly was, through patient, ongoing analysis combining Voyager 1's own continuous data stream with independent observations from other missions and theoretical modeling, refining the underlying physical picture piece by piece until the observed data and the theoretical model finally align cleanly. There's a genuinely sobering practical reality layered underneath this entire ongoing investigation. And it's worth understanding clearly, because it adds real urgency to the work currently being done. Voyager 1 is not going to be capable of collecting this kind of data indefinitely. The spacecraft's power source, a radioisotope thermoelectric generator relying on the steady, predictable decay of a plutonium core, loses a small amount of usable power every single year. A decline that cannot be reversed, repaired, or refueled from Earth. Both Voyager spacecraft lose approximately 4 watts of power annually, a figure that sounds small in isolation but represents a hard, unforgiving ceiling on a spacecraft that launched with a finite power budget nearly 5 decades ago and has never once been serviced by human hands. NASA's engineering team has spent years carefully, deliberately shutting down one non-essential instrument after another, specifically to keep the spacecraft's most scientifically valuable remaining instruments operational for as long as physically possible, a slow, methodical triage process that has been unfolding continuously since the late 1980s. As of recent mission updates, Voyager 1 is down to just 2 functioning science instruments, its magnetometer and its plasma wave subsystem, the exact 2 instruments responsible for detecting and documenting this entire ongoing magnetic field mystery in the first place. Every other instrument the spacecraft originally launched with, its cosmic ray subsystem, its low-energy charged particle detector, and the rest of its original 10-instrument suite, has already been powered down permanently, sacrificed piece by piece to keep these final 2 operational. Every additional year, those 2 instruments managed to keep operating represents genuinely irreplaceable data, since there is no successor mission currently positioned anywhere near this specific region of interstellar space, and building and launching a new spacecraft capable of reaching a comparable distance would take many decades, even if such a mission were funded and approved today. Voyager 2, Voyager 1's twin, is following its own separate trajectory through a different region of interstellar space entirely, offering a valuable second data point, but not a direct substitute for whatever Voyager 1 itself happens to be sitting inside at any given moment. That reality is precisely why researchers are treating this ongoing anomaly with such careful, sustained attention rather than setting it aside as a lower priority curiosity. Every additional data point Voyager 1 manages to send back extends what is likely to remain, for decades or longer, humanity's only direct physical record of how our sun's activity actually reaches out and influences the true interstellar medium beyond the heliosphere's boundary. Understanding precisely why this specific magnetic disturbance has persisted 5 times longer than either of the 2 previous events isn't simply an academic curiosity about one spacecraft's readings. It's directly informing broader models of how the entire heliosphere interacts with the surrounding galaxy, models that matter for understanding everything, from how cosmic rays reach our own solar system to how the sun's protective bubble might behave differently as it moves through different regions of the Milky Way over the coming millions of years. So here's where this genuinely currently stands, based on real, published, peer-reviewed research, rather than any exaggerated framing. Since 2020, Voyager 1 has been recording a sustained, unusually persistent enhancement in the strength of the magnetic field surrounding it in interstellar space, an event that has now lasted more than 5 years and covered over 1 billion miles of the spacecraft's own outward journey, dramatically longer and more spatially extensive than either of the 2 comparable disturbances recorded in 2012 and 2014. The leading explanation remains a refined version of the established piston model, tying the disturbance back to unusually strong solar activity during solar cycle 24. Though researchers themselves have been directly, publicly candid that the persistence of this particular event initially led some members of the scientific team to seriously question whether the sun was even the true source at all. That's not a manufactured mystery. That's an honest, ongoing scientific investigation, still actively being refined and published in peer-reviewed journals as recently as 2026, using data from the only spacecraft humanity has ever had stationed in this specific, otherwise completely inaccessible region of space. Voyager 1 is still out there right now, 14 billion miles from Earth, and moving farther every single second. Its 2 remaining working instruments continuing to record exactly what the true edge of our solar system's influence actually looks like, in real time as it happens. Whatever combination of solar activity and interstellar physics is ultimately responsible for this specific 5-year magnetic anomaly, the spacecraft responsible for detecting it has already outlived its original mission by nearly 5 decades. And it's still, even now, sending back genuinely new, genuinely unresolved science that nobody anywhere else in the solar system has any way of directly measuring for themselves. If you want the real, peer-reviewed science behind stories like this, the kind that respects genuine, ongoing scientific uncertainty without dressing it up as something it isn't, subscribe and turn on notifications, because researchers are still actively analyzing this data right now, and we'll bring you the next update on Voyager 1's interstellar magnetic mystery the moment new findings are published.